So up to this day, we've talked to amplifiers and circuits, and we've talked a lot about a lot of the DC properties, a little bit of the dynamical properties, but I want to get a little bit further into this and talk about a circuit that's just basically a very simple structure that allows you to get some basic first-order dynamics out of the structure. And in fact, if it has first-order dynamics, it makes sense to actually use it as a filter, right? I mean, instead of like trying to make something and then make something more idealized. So these are the kinds of structures you would think about. So you might imagine, let's say I start with an OTA structure that we've been building, 5 transistor, 9 transistor. And for today's discussion, really it won't matter. And it obviously has a bias voltage for the bias transistor on the NFET, which of course sets a bias current. Okay, and so there'll be some bias current we're going to work with there, which will be I bias in this case. And then I'm going to look at what is the input, what is the input-output voltage. What's useful about this circuit is without this capacitor, we would know to solve this because of the high gain that the output voltage is roughly equal to the input voltage. So we expect at DC we're going to get something that's going to be roughly equal, right? And we'll see this as we go through the equations even further. But you kind of expect that. But the question is, the minute I add a capacitance, and we always have capacitance, there's no way around this. You always get some capacitance down to some DC potential. And how much is the question, and how much I have to deal with. But I'm always going to see it in these circuits, and it's always going to give me a first-order dynamic, and I can either fight that dynamic, or I can try to work with that dynamic. I tend to be an optimist. I like to go with the second one. So we'll see what we can do there. That being said, we're going to go with, let's say, well, let's just analyze the circuit, right? And you begin, well, the best thing to do is do KCL around this node here, which is then this capacitance and the current going into it. Well, the current going into it is a tanh, so we already know where we're going there. And you get a nice differential equation of the differential of the output voltage and input and output voltage. There also should be a kappa in there, which I realize I just missed, but I'm sure you're all correcting it. And you're like, yay, I've got my differential equation, I'm done, I just solve it, right? And you could do that, and this is an equation, by the way, that you can actually solve analytically. It's for those who are curious. But it's actually, typically we don't want to go through that, and circuits are going to get a lot more complicated as we go. So you might ask, well, how do I start thinking about the intuition of the circuit? And there's kind of multiple places you want to look at. And the first one people will talk about is what happens when stuff is small. And we've even talked about what are small signal models to some extent. But this kind of gives you a really solid idea of what do we mean by when we talk about small. And in this case, what you see is we have tanh of a whole bunch of things. Well, the tanh of this, when it's near zero, near the middle of the tanh, is actually going to be roughly just that term. So if I linearize the tanh, it just gives me what's inside here. And so as a result, you linearize this, and I just get this term in front, kappa times I bias, the I bias from there, over 2UT, times the difference of two inputs. So it actually gives you exactly what you'd expect for a transconductance amplifier. The difference of the input voltage gives you an output current. All that makes sense. So sometimes we'll talk about this as being some GM of that structure. Particularly makes sense because it's going gate voltage into the structure. So there's some reasons to think about it. Well, if I actually look at this gives me a nice linearized approach. I can actually now put this back into the differential equation, and what I find is I get a differential equation of a very canonical form, which is I get a tau times the derivative plus the output equals the input. This is a classic first order low pass filter with basically a gain of 1. Such that I know my tau, by the way, the interesting thing, tau is set by bias current, and that's actually a parameter I have to work with. This is kind of cool, actually. If I want to think about it in terms of GM, just to kind of go, is it a real RC time constant? Yes, in fact it is, and you can kind of think about this. So, and I can then do a step response and do a small input, and in fact what I will get, and put a step at this point, I will get a nice sort of typical, if you had an R and a C roll-off, you get exactly this. But now this is actually being done with this amplifier structure. And again, the same sort of thing, it falls on the other side. You get both sides, they look symmetric, they are symmetric. If it's linear, it has to be symmetric. If it's linear, it means that if I made the amplitude twice as big within its linear region, it should look the same, just scaled, right? And also, and all the superposition properties hold as well. So we have a whole bunch of opportunities there. But then you might go, okay, well, small seems kind of small maybe, because UT is 25 millivolts. 2 times that gives me about 15 millivolts. You're like, kappa, maybe 70, maybe 100 if I stretch it. And there's a lot of times when maybe I want things bigger than that. So like, what happens when I have bigger signals? And so we can take the reverse case. Let's say that these gets really large. And for a tangent, at the extreme edges of a tangent, I get plus or minus the thing that's in front of it, plus or minus 1, which means it's plus or minus the bias current. Well, this also is something you see a lot, and it actually shows up so often it's given a name for amplifiers. It's called slew rate, or slewing behavior, and you characterize it by slew rate. And the reason you talk about a slew rate is actually, if I were to say this is my analysis, this is my current, let me just analyze the function, and I could see dV out dt is going to be either plus or minus that bias current. So if I solve this, I'm going to see something that's just going to change linearly with time, where the slope will actually be related to the bias current in the C. And this is actually 1 over the slew rate, I realize, but that's what you would, those are the two, it's that ratio of the two things that is important. And the slew rate changes with, definitely changes with bias, so it's going to change in the bias current. And you might say, well, does that really what it looks like? We'll take the same amplifier and we ran a large signal, almost a volt, on a 5-volt supply amplifier. Sitting here, and the step occurred right at this edge. And now it turns out, if I look at it, it looks like it's got this long straight line, and then it returns to. Compare that to this function, and you can see there's quite a bit of very different roll-off. In fact, here it of course starts linear because every function in some region looks linear when you start it, but it definitely has this nice sort of exponential behavior. Here is linear over, and this is only if you look at the axis here. This is 300 plus or minus 30 millivolts. This is over a volt, and it just goes constant for a very long time, and then moves to the DC, to its solution in a nice, simple way. So you'll constantly see things in terms of slew rate being one way to characterize the nonlinearity. It's not the only way nonlinearity shows up, but this is one for a particular function, particularly seen when you use tangent type functions. But it's important to kind of see the entire structure, because you might say, oh, I never want to have slew rate effects. Well, what if I have a circuit where I really want to have something that changes linearly versus time? Maybe I do. It'll all depend on what you're trying to build and what the resources that you have available to build it. And so it's important to kind of keep the perspective wide open and to kind of see the dynamics as a whole, independent of kind of what you think in a starting application you think you're going to need. It's worth to kind of look at the whole picture.